This conference will now be recorded.
Okay, so what we're going to be demonstrating with you today is how to use the indexed machining to program 4-axis on a rotary head instead of a rotary table in RhinoCam. So you would be able to tilt the head to different orientations, as you pointed out in this particular, PDF file, where you want to be able to keep the tool parallel to these side walls so you can machine those undercuts, which typically you wouldn't be able to do it just on a 3-axis setup, right?
That's correct. That's the abilities that we're looking for.
All right, great. So I'm going to go ahead and open up Rhinoceros. The file you sent us was probably done and saved in Rhino 5, so I'm just going to bring it up in Rhino 5. I'll just select the file here and then click Open. So the RhinoCam 2019 plugin works both in Rhino 5 and Rhino 6. We have separate installers for each version of them. Okay, so we have this part in here. The first step you want to make sure is you are working in the correct units and also the orientation from which you're going to be machining the part. And then we'll go through the process of defining the machine tool. So it looks like you have the part already defined in millimeter units. And then if you take a look at it looking down from the top view, based on the orientation of the part and the machine tool that you have, since you mentioned during one of our previous emails that the rotation of the head is about the y-axis. Is that correct?
That's correct, yes. So
all right.
We'll need to rotate that.
Based on that, the orientation of the part looks correct because you can tilt the tool about the y-axis to be able to cut these, the draft that you have in here, and also this through slot that you have on the part. Yes. So we'll go through the process of defining the machine tool. So we're going to pick a manual definition and select 4-axis. And for the configuration, since this is going to be a rotary head, which means the rotation is on the spindle where it's going to tilt the tool, we'll pick configuration as head. Okay?
Yes,
and
that's fine.
The
I understand that.
rotary axis is going to be defined about the y-axis based on how your machine tool is built.
Yes.
So that would be a plus y, or it could be minus y, depending on how the rotations are handled. So the plus and minus is determined on the direction of rotation. So if you select plus y, you point your thumb in the direction of this arrow in here, rotational axis. So as you roll your wrist towards you, that'll output a positive angle. So if the tool is perpendicular or normal to this face, you would see a positive angle, like a B-axis angle being output for this.
Yes.
And if the tool is normal to, or you're cutting the slot, you might get a negative angle because you're rotating that direction. So the positive and negative, depending on how your controls are set up on the machine, you can pick Y positive or Y negative.
Okay, I'll have to check that once the machine arrives. Okay. Yeah. I'm not 100%.
So, yeah, we basically output based on the right-hand thumb rule here. So now, if you go ahead and for 4-axis and 5-axis, anytime you have a rotary head, you need to compensate for a gauge length, which is the distance from the tip of the tool to the pivot point. So when the tool is perpendicular to the XY plane, and when the tool is tilted, you need to compensate for the gauge length. So you can clear this checkbox in here. So it's going to be allowing you to define the gauge length parameters. So this is the distance from the pivot point to the spindle face, plus you define the tool length when you define the tool, the distance from the spindle face to the tip of the tool. So what you're entering here is basically the gauge length from the pivoting point down to the spindle face.
Okay.
So that parameter will be constant for a given head on a CNC machine tool, but what would be a variable would be the tool length, depending on the size of tool that you're going to be using, and then how far it's going to be sticking out from the spindle face.
Okay, I understand that.
So this value, if you put it to 0, which means that the controller does the compensation, so we don't have to compensate it from the CAM product here, like an RTCP on, or certain controllers call it RTCP or like G48.1, or so each controller has its own way of handling it.
Okay.
And we can also specify the limits for the B axis.
Yeah, in this situation, it'll do plus 90 minus 90.
Okay, so we can set the user-defined limits. Go minus 90 to plus 90. So on some machines, it could go maybe minus 105 or minus 110 to plus 110, depending on how the machine is built and the controls are set up.
Yep.
Okay, so we define this. So the machine tool definition, that completes the machine tool definition process. The next step is to select the post processor here. Based on the sample that you sent us here for the Syntex 6, I've set up a post for metric units, which uses G71 on this particular machine. Some machines use G21, this uses G71, so to represent the units. And over here, we've configured the post for the indexed operations right in here in the setup. So it'll output the rotation axis angle. The post is configured. We can set the maximum spindle and the feed rates. And then the axis code, so if I go into multi-axis motion, if it's going to be called a B axis, I can define it as a B axis, or if it's going to be called an A axis.
Yes, okay.
Okay, so the primary would be defined as B. So that's pretty much it, what I need to do for the post right now. And then we'll define our workpiece. We'll go to stock and box stock, and this computes the extents, length, width, and the height. So 800 is the distance along the X, which is the length, 500 is on the Y, and then 200 is the height or the thickness.
Okay.
And we're now ready to start programming our toolpaths. So before we do that, we want to make sure that the origin, so we don't want to keep changing the origin. So once you establish the origin, it'll be the same for all your toolpaths. So whether you rotate the head or you change the setups. So is this a good place to leave the origin, the southwest corner and the bottom?
For clocking purposes, yeah, that'll be fine. That'll be okay.
Okay. All right, perfect. Now, we'll go ahead and define some tools in here. Would you have any recommendation of what size tools should we be using for this part?
Oh, on that part, you're probably going to be looking at like a 20 millimeter.
Flat mill for roughing and then a ball mill for finishing?
Yes, yes.
Okay, so we'll go ahead and add a flat mill 20 millimeter. And we can set the tool length from the tip to the spindle face. That'll add that to the gauge length when we apply a gauge length. So what you put in for the tool length is going to be, has to be correct, the value, if you would like the cam to compensate for the gauge length.
Okay.
And then you specify the tool number. If you have an automatic tool changer, if you need to use a coolant, you can specify a coolant type in here. And then in the feeds and speeds, you can use the built-in feed speeds calculator. So it reads the maximum spindle RPM and the cut feed rate from the post that we've defined in here. And then you can use the spindle RPM that you like to use for the roughing. I could say I want to go with 15,000 RPM. And you can use your cut feed rate. I could say 1,500 millimeters per minute. We'll accept that. We'll save this out as a new tool. So we have a flat mill tool defined. If you want to rename it, you can just select it and say flat mill 20 millimeter.
Yes. Okay.
Okay, so we have a tool defined. So we want to first start with the roughing process. We'll use 3-axis roughing.
Yes.
And before I get into roughing, I wanted to point out, like by default, the setup that you have here, your B is at 0, which means it's parallel to the XY plane. So like any normal 2- and 3-axis operation. So we will be creating additional setups for each orientation. So we'll first do a roughing looking down from the top. So we'll do a roughing 3-axis and horizontal roughing, since you have these, fillets in here, the sculpted features in here. So we can't just do like a 2D operation. So we have to do a 3-axis operation.
Yep.
And then you can select a tool for it. Feed speeds can be set right here or automatically loaded from the tool. If you need to set a coolant, you can specify it. Your clearance is by default set to automatic, so it's going to clear the maximum height of the part of the stock by a safe distance. You can also change the safe distance. In the cutting parameters, you can specify your tolerances for roughing, and then specify the amount of stock that you'd like to leave after it's being roughed out. I could say 0.5 millimeter. Specify our step over control. And in the cut levels tab, you can specify how far down you want it to cut. I could restrict it to a certain depth in here. I could say I want to just go right up to that particular plane, or maybe, go slightly below that, right?
Yes.
depending on how long the tool is and how far down you can cut to. So I could say just leave it right down at the point and specify any engage and retracts and then generate it. So in this process, it's going to create a 3-axis roughing toolpath. So it's going to do roughing in levels or roughing in layers, also called horizontal roughing or Z-level roughing.
Yes. Okay.
And since we chose the depth to be only 300 millimeters, it's stopping right there. And you can notice that the cutter is also able to get into some of these pockets as you look at it down from the top. So if you want to mask those pockets from being machined, one of the things you could do here in Rhino is maybe add a new layer, and you can select, you can patch this surface here. You can say surface using edge curves.
Yep.
And I can just pick those 4 edges. You can just cap them.
Yep.
And then regenerate this toolpath.
And then it'll just leave that area alone.
Yes, because we're going to be tilting the tool to that face to machine some of those features, right?
Yes.
So now you can notice that it's not going to be cutting any of those pockets or getting into those pockets. So let's go ahead and run a simulation in here. Now I can have the simulation even go faster. If I take a look at the units here, I can just set it to, from a micron, I can just drop it down a little bit here. So that'll make the simulation even go faster in RhinoCam. So it's detecting a holder or a shank collision in here. I'm going to click yes to accept it. So I can see it's rubbing against the stock. Since we cutting down 100 millimeters, so you can see a collision right there.
Yeah, we're probably going to be better to lengthen the tool, to have a longer tool.
So we wanted to go maybe 120. Change that. We'll save it as to tool. We'll regenerate the path. Do you have any questions so far?
No, I'm following all that.
Okay, so let me go back and rerun the simulation. We'll just do a pause, simulate to end. Okay, so again, you're seeing a holder collision or a shank collision is because the shank is rubbing against the stock. So
yeah, because the flute length isn't quite long enough there.
You got it. So I can change the shoulder length to maybe 100, flute length to maybe 110 and 100. So that'll take care of that. So these are some of the new things we've added in 2019 to determine the shank or the holder collisions. So it helps the programmer to identify and make sure the tools are right before cutting it.
Yep.
Okay.
Do you allow for like stepped cutters? Because sometimes a lot of the cutters we get are it's only the tip that's cut in, but the shank is clear.
Mm-hmm. Okay, so now we want to go ahead and program some of these sites in here, right?
Yes.
Okay, so first thing is we want to go ahead and cut this out in here, this angle. So we wanted to add a new setup in here. So you can say setup, and then choose a new setup in here. And you can choose how you want to orient it. So if you know this angle, you can type in the angle and rotate it, or I can select a surface. I can just go pick that face. So now the Z is going to be normal to that face. However, we want it to be parallel, so I can, rotate it about the Y-axis or X-axis by minus 90. In this case, it'll be Y. So that'll basically make it parallel to that. Okay?
Okay, yep. That was simple.
Now, that was a new setup. So we just go down to setup and then click on a new setup to add it, and then we can orient the coordinate system. So basically, the tool axis is now oriented. So if you want to go from a roughing to a finishing operation in here, we can choose a finishing operation, or if you want to do a roughing operation, we could do one with a boundary. We can select a region for it. One of the things I would like to do is if you want to add a region, I could even take the C-plane that we have here, and do a rotate, and rotate it by the angle that this is in. So if this is about like 10-degree rotation on the Y, you can say Y-axis, and you specify the angle to be rotated. I can say 10. So you're rotating it by 10 degrees, so you can see that the X and Y are parallel to it. So now if you go to set view, and you can say set view to plan, so you can see now these features are visible to you for cutting it, right?
Yes.
And if you want to define a machining region, I could go ahead and select, I can create a region in here. So this is the area I want to put a region for. And now you can notice that the region what you created is parallel to that inclined plane that you defined.
Yep.
I can do a roughing operation. So rather than doing a horizontal roughing, I could use a re-roughing operation in here. So under setup number 2, select horizontal re-roughing, and I can pick this as the area to contain. Pick the same tool, or I can go with a smaller tool. You know, you can see now the clearance plane is automatically oriented.
Yes.
And then select the parameters for your cutting. You can specify the amount of stock you want to leave on the sidewall. I could say I want to take it down to like 0.2 millimeters. You can control the cut levels, step downs, and then I'll pick generate. So in this process, the re-roughing actually looks at the in-process stock, which is the material that's being left from the previous step. So even though you machined it looking down from the top, now you have tilted it. So it takes into account the in-process stock, and it's only clearing material. You can see there's more material down as you're cutting down in levels.
Okay.
And when we post it, we'll compute the angles and output it for going from the setup 1 to setup 2. So once we are through with the roughing, if you want to go ahead and program a finishing cut while you're in the same setup, you can go from a roughing operation to a finishing. So here I could use a 3-axis horizontal finishing or a Z-level finishing. Make a selection for the tool. You probably want to use like a radius tool, like a ball mill.
Yeah, a ball mill.
And would that be like a 12 millimeter or larger than that?
Probably because they're changeable heads. It'll probably be a 20 millimeter ball for the size of that radius that's in there.
So we'll put in a 20 millimeter
radius.
Okay.
You'll have to change the flute length as well, otherwise you might get a collision error.
Yep, I just did it right here.
No. Okay.
Okay, so we'll go ahead and pick this tool. We'll use the same parameters for feet and speeds and clearance. So, in the cutting parameters, you can specify how fine you want the cutter to step. You could say you want to go % tool diameter, or at distance, you could say you only want to step down like 3 millimeter per pass.
Yep.
And, generate. So since we use this as a containment, you'll notice that the tool path is going to stay within that area. So that's giving you your finishing cut. If you take a look at it from the front view, you can see you're at an angle. And then we can also add another pass in here to do like a finishing operation, like a parallel finishing. If you want to do a 3-axis, add an additional operation, like a parallel finishing. Yes. You can use other operations too, any of the 3-axis advanced operations. So one of the things I could do is just to finish these radius, I could do like a between curve machining.
Yep.
So I'm going to extract these 2 curve edges in here. And
now those between curves, is it either side of the curve or is it actually up to the tip of the
the tool tip is going to stay upright up to this area, so I'm going to use a gumball to maybe move it out by like 10 millimeters.
Okay, yep.
And we'll check the direction of these 2 curves, make sure they're flowing in the same direction. So now I'll add a 3-axis between 2 curve machining. And I'll pick this first curve. And I want to flow from the top down to the bottom. And we'll specify a step over distance in here.
Yep.
Then generate it. So with the 10-degree tilt that you have, you can see it's riding up on the surface too right here, on the between 2 curve. So you can start from the top. So instead of the horizontal finishing, you could probably have done with just one operation in here. Or if you just wanted to do the fillet section in the bottom, you could have just slightly offset the curve.
Yes.
So it doesn't right along the edge on the top. Okay?
Yeah, that's good.
All right. So now I'll just do a file save. So the work is automatically saved. So here I'll just do a save as so I don't overwrite your original file. Just call it revision 1. Okay. Now this section here, you can rotate it to a different orientation if you want to cut it from a different angle, the tool,
yep.
right? So let's, sorry,
yeah,
go
the
ahead.
reason I normally tip the tool is just to keep it off the very bottom of the ball. So if I'm cutting with a ball nose, because then it's not, because it's 0 speed on the very tip of the tool, which then wears the tool quite quickly, plus you don't get as good a finish as well.
Yep. So we'll add a new, I'm going to go ahead and then delete this operation out for now. So we'll add a new setup in here. So we want to put it back to the machine coordinates. And now I can select a surface and say I want to put it normal to that face. So the tool is perpendicular to this face.
Yes.
And we can now program a roughing toolpath, or we could do a finishing toolpath for this section in here. So since this is planar, you could even just do like a 2-axis operation by picking a boundary in here. So I'm going to just pick a boundary curve. And we can just do a 2-axis operation.
Yes.
So we'll select 2-axis. We could do facing. Select this as the boundary containment. And then use the flat mill. You could choose whether you want to go parallel to X or Y. I could say linear cuts parallel to Y. So angle would be 90 degrees. Specify a step over and generate it. So that gets you a facing toolpath, and you can probably use a larger step over than you could do a 45 or 50% step over. So that lets you clear that material out. And again, if you take a look at it from the front view, you can see the tool is oriented.
Yep, looks good.
And now we can apply a similar toolpath in here for finishing these sections in here as well, right?
Yes.
You want to flow along this. So again, if you want to do
I'd normally go over with the same cutter you've got there, the flat mill, and then go over the ball afterwards. I just leave a little bit extra on there, say 0.6.
Okay. Okay. So one of the ways we could program this would be using like a 3-axis. We could do between 2 curves.
Yes.
And I can pick this edge. And just go pick this edge right in here, depending on how far I want it to cut, right? So
yes.
I can pick that one. So I might be getting too close to this edge, so might be better if I can just, offset this out. So take this curve in here, and I can offset it out by another, 10 millimeters.
Yep.
And I can create a curve. It goes from here to here. So now I could use this curve I just created, and this right here. And with the same flat mill, you want to leave some stock in here. I could say leave like 0.2 millimeters. So that's basically going to generate a toolpath that flows between the 2 curves. So you can see that this is not a very desirable toolpath, and it's going to, with this angle go on it. So because you have these bumps in here on the model, so you might want to probably do like a parallel finishing operation. You could basically just use a boundary in here. I could use a parallel finishing might work better in this case.
Yes.
So I'm going to switch, delete this one out, and then we'll do a 3-axis parallel finishing. I'll just pick these areas in here. So just a closed loop. And if you wanted to keep it against the wall, you just have to shorten this a little bit.
Yep.
But you can see it's checking against it. It's not going to gouge into that wall. So now you have a parallel finishing toolpath, and you can choose which way you want it to cut. So right now it's going parallel to X, but if you want to change it to go parallel to Y, we could change it. Would that work?
Yes, that's okay.
Yep. And then also I'm going to change the amount of stock to leave. I believe I set it to 0. So here I'm going to say leave 0.2 millimeters in stock. So it's leaving some stock on the floor, and then you can go back and finish it with a different operation. So by doing indexed, what you're doing is you're basically locking the head to a given orientation and then programming it.
And then machining from there, yeah.
So the next step would be to add a finishing cut around this area here to clean it up, right?
Yep. I'd normally do like a little Z level around there.
Okay. So you want to probably do a Z level finishing by keeping the tool. You want to keep it perpendicular to it, like do the XY plane.
It should be vertical now.
I've vertical.
Put that vertically.
Yep. Go back and add a new setup. Put it back to the world coordinate system orientation in here. And we could do a 3-axis horizontal finishing. And you could select this as the boundary. And pick the ball mill tool. So that will give you a horizontal finishing toolpath.
Yes.
So you can take advantage of all of your 2- and 3-axis operations when you do index 4-axis with the head.
Yeah, that's exactly what we're looking for. That's.
And you can go back and clean this up with a 3-axis operation like a curve machining. So just to go around to clean it up.
Just go around the edge.
Yep. So it's select my control geometry. So I'm just going to go pick this here. And if the radius is matching exactly what you have, it will just give you one nice pass to go clean it up.
Yep.
Or if you want to do additional passes, we can step it over as well.
Yep. That demonstrates.
All right.
Pretty clearly.
So now let's focus on this section in here, right? The slot in here.
Yes.
So we could go back and do another setup and select normal to this face. So now you have the tool tilted, and you want to machine the slot. So we want to figure out, what is the width of the slot in here. That's about 6 millimeters. So you can probably use a 6 millimeter end mill. Yes. And we can program a profile cut to cut it in one pass in multiple steps. So I can just pick that edge, create a tool, a 6 mil flat tool. And this doesn't have to be that long, so I can say just 60 millimeters. We'll save this up. That's a new tool. And then everything else would be very similar. And you can choose the cut levels in here. So when you measure the depth, it's going to be along the tilted plane. Okay. And you can say you want to go in multiple steps of 3 millimeters each. You can control your entry and exit however you want it to. Lead in, lead out, so we can have a slight, retract outside, so it gives you a nice clean edge, and then generate it. So that'll give you a profile cut. At that angle.
Yep, perfect.
And now you want to go ahead and take care of these areas in here. So you probably would want to go ahead and clear off this material. So we want to go ahead and add a new setup, and we want to go normal to the surface. So that basically orients the tool normal to that surface. And I could add a facing operation, so just copy one of these facing operations from here. And we'll pick those 4 edges. And then generate a path. So that'll give us a facing to clear that material out. If you wanted to do a roughing operation, you could do it. So to do like a re-roughing to remove the excess symmetry on this orientation.
Yep.
And once you're through with the facing, you want to do this pocket in here, 2-axis pocketing. You can pick this edge. And then I could still do the same cutter. And then all I had to do is pick the depth in here.
Okay.
I can also say determine using 3D models, so it'll figure out how deep the pocket is. If you want to do rough and finishing all in one operation, you can set the stock to 0. So that gives you the pocket operation.
Yep.
And then finally, you have these holes. We could check the diameter for these. That's 9.9. That's 5 millimeters. So if you have a tool that matches those hole sizes, you could do drilling operations.
Yes.
You could go into hole machining and drilling. I could say select holes on a face. I'll pick the face right here. And I can just grab the 6 millimeter tool. And I'm going to go specify my cutting parameters in here. Pick the depth. So I want to go from here. I can pick a point, a reference, and go down to this one. And then you can specify how do you want to sort it. Go directional sort. So you want to minimize the number of transfers and retracts. And you can do a zig or zigzag for the cut pattern. So that gives you a drill operation. Or if you want to do like a pocket and a profile, you can do that.
Yes.
So once you have all these toolpaths programmed, you would want to do a post or post all. So you save off the file, select the machining job, right-click and post all. It's just warned saying that it's a multi-axis toolpath, so you want to say, do not show this again, and then pick post. And there's your posted code. So start with B0. And we can do a search for the next. So you can see the startup code is right here. G90 absolute programming, G71 millimeters, G54 is your work offset, G53Z calls up to tool number. And you can see the B values. So it goes to 10 degrees for the B.
Yep.
And B goes to -10 for the other side. And then we have B going to 70 degrees to cut the other face.
Yes, to do the end.
Yep. And then B0 at the very end before you cancel it out. And in this case, we haven't applied any gauge length in here. So we'll show you an example with a gauge length. So let's take a look at one of the operations where we need a gauge length to be output. So when you put in a gauge length, so let's say the tool is, we have the tool length in here. Let's look at this operation in here. Well, you see that the tool length is 120 millimeters. So let's say the gauge length is about 100 millimeters. I'll add a 100 millimeters gauge length, and all I have to do is repost it.
And it's done.
And I'm gonna. So now you'll notice that it'll compensate and apply the gauge length in the posted code when it goes from one orientation to the other. So as the B rotates in here, so this is with the gauge length, and we'll look at the output without the gauge length in here. So if you notice, compare the two, you'll see that the Z values are changing with the gauge length being applied, and even the X values could be changing. So compare this line here with this line right here.
So that line there, yes.
You can see it starts applying the gauge length even right above it, so it compensates for it. So RhinoCam will automatically figure out what the coordinates need to be in order for the tip to be at the correct location based on the gauge length that you put. So if the gauge length is not specified, which means it's 0, then the tool length also doesn't get added to it. So, which means machines that where the control can handle the gauge length.
Okay, and I'll need to figure that out once the machine's here and I'm a bit more familiar with it.
Would you have any questions so far on the demo?
No, that's brilliant. that's what I needed to see, is that the software could handle that fourth axis. So, yeah, thank you very much for that demonstration. Yep. And yep, then we'll get that underway. I'll contact your sales team, and then we'll get our current version.
So this
updated.
is all accomplished in the Pro configuration to do this. So if you need simultaneous 5-axis or simultaneous 4-axis, then that would require the premium. So for example, if you want to take this surface in here and you want to keep the tool normal to it, then that would require you to have the the premium configuration. So I can give you a quick example for that here. So let's say I wanted to put a new layer, and I'll extract this edge. And I'll just create a surface from this edge here. So I'll do a surface, extrude, curve, straight. We'll go across to that edge right here. I'll check the direction. I want to flip the direction.
Okay.
Okay, so now...
Is that important to flip the direction?
You could do it in the same way in RhinoCam as well. So if you select, for example, a surface normal machining, when you pick a surface, you can actually set the normal directions you can check. So if you already have it set in Rhino, you don't have a flip.
Okay, yep.
Just makes it easier. And you can choose the tool for it. You can specify your cut parameters in here.
Yes.
Step overs, and then I'll put generate. So in this case, I'm not accounting for this features on the inside right here. So I can choose to lock it to 4-axis. And then generate the path. So you'll notice that the secondary axis angles is changing. You see -59, so it's constantly rotating. Your B is rotating as you're cutting it. So that would be in the premium configuration. So I haven't put in any collision or gout check against the sidewall.
Oh yeah, no, I understand
the
that.
rotation of the head. So if you need the continuous rotation of the head, that would require you to have the premium configuration. So that's the difference between indexed versus continuous, where it'll be able to move all 4 axes simultaneously.
Okay, that's probably something we'll look at later on, but yeah, at the moment, it's not a particular need we need at the moment. But I can see it would be very useful for finishing purposes.